Picture this. You're standing at the edge of a cliff, looking down at what should be an impossible drop. October 22nd, 2025. That's the date everything changed, or maybe everything we thought we understood just shattered. Google just did something that has physicists checking their math, philosophers questioning reality, and some scientists genuinely terrified. They didn't just build a faster computer. As it turns out, they might have just proven that the universe operates on rules we barely comprehended. Here's the thing about quantum computers: they don't play by the same rules as your laptop. Your laptop? It's like a very determined ant walking through a maze, trying every path one by one. But quantum computers, they're more like, let me picture that in a different way. They're like a ghost that walks through all the walls at once, experiencing every possible path simultaneously, and then just appears at the exit with the answer. But what Google's Willow chip just accomplished, that's not just walking through walls. That's rewriting the architecture of the building while you're inside it. What people don't realize is this isn't about faster phones or better video games. This is about breaking thermodynamic laws that have governed reality for 200 years. This is about solving problems that would take the universe's entire lifespan in 5 minutes. So, check it out. And let me tell you something. When you flip a coin, it's either heads or tails, right? Classical physics says that coin is definitely one or the other, we just don't know which until we look. But quantum physics? Quantum physics says, actually, that coin can be both heads and tails at the same time. Not might be one or the other. Not we don't know yet. It is both. Simultaneously, until you observe it. This is called superposition. And it's not science fiction, it's just science. And it's weird. Richard Feynman, one of the greatest physicists who ever lived, once said, "If you think you understand quantum mechanics, you don't understand quantum mechanics." But here's where it gets interesting. Google's Willow chip has 105 qubits. Now, a qubit is like a quantum coin. It can be 0 and 1 at the same time. The most astounding fact is each additional qubit doesn't just add power, it doubles it. So 105 qubits aren't just 105 times more powerful than one qubit. They're 2 to the power of 105 times more powerful. That's more possibilities than there are atoms in the observable universe. Let's talk about what Willow actually did. They ran an algorithm called quantum echoes. Think of it like this. Imagine you throw a stone into a perfectly still pond. Ripples spread out in all directions. Now, imagine running that movie backwards, trying to get all those ripples to converge back to the exact point where the stone hit. In the real world, impossible. The ripples dissipate. Entropy wins, information scatters. But quantum systems can do something extraordinary. They can run processes forward, then actually run them backward. Google took their qubits, ran a series of quantum operations forward, then here's the clever part. They deliberately poked one qubit in the middle of this process, like flicking one domino in an elaborate setup. Then they ran everything backward and measured how that tiny disturbance rippled through the entire quantum system. This lets them extract information about molecular structures that conventional tools simply cannot see. They're measuring something called an out-of-time order correlator, essentially mapping how quantum information spreads and scrambles through a system. In fact, Willow solved this particular computational challenge in under 5 minutes. The world's fastest classical supercomputer, it would take 10 septillion years. That's 10 followed by 24 zeros. That's longer than the current age of the universe, by a factor so large it makes my brain hurt. But wait, there's more to this story. What people don't realize is this is the first verifiable quantum advantage. Previous claims of quantum supremacy couldn't be independently checked. It was like someone saying, "I calculated the trillionth digit of pi in my head," even if they give you an answer. How do you verify it without doing the calculation yourself? With quantum echoes, they can run the same experiment on smaller scales using classical computers, verify the method works, then scale it up to where classical computers can't follow. It's verifiable, it's repeatable, it's real, and here's the kicker. They partnered with UC Berkeley and used this to predict molecular structures 15 atoms in one molecule, 28 inches another. Then they verified their predictions using actual nuclear magnetic resonance spectroscopy in the lab. The predictions matched perfectly. Not approximately, perfectly. Now, let's talk about something that sounds insane but might actually be true. Some physicists, serious, credentialed, peer-reviewed physicists, think that quantum computers might be accessing parallel universes to perform their calculations. So check it out. There's this interpretation of quantum mechanics called the many worlds interpretation, proposed by physicist Hugh Everett and championed by David Deutsch. It suggests that every time a quantum event happens, every time that coin lands, every time a particle chooses a path, the universe splits. All possible outcomes happen, but in separate parallel universes. Right now, in this interpretation, there are infinite versions of you. One where you clicked on this video, one where you didn't. One where you became a professional musician instead of whatever you're doing now. One where humanity never invented the wheel. Now here's where it gets wild. When a quantum computer explores all possible solutions simultaneously, what people don't realize is it might be farming out those calculations across parallel universes. Imagine billions of versions of Willow, each in its own universe, each solving a piece of the puzzle, and then, somehow, the answer coalesces back into our reality. Think about that for a second. We might have just built a device that borrows computational power from parallel universes. David Deutsch himself has suggested that quantum computers provide indirect evidence for the multiverse. His argument? There aren't enough particles in our observable universe to store all the intermediate states that a quantum computer explores. So where are those calculations happening? His answer: in parallel universes. Now, I know what you're thinking. That sounds like science fiction. And you're right to be skeptical. The good thing about science is that it's true whether or not you believe in it. But we're talking about a serious hypothesis from serious scientists. Actually, there's another interpretation, the Copenhagen interpretation, which says quantum states are just probabilities, and when you measure them, the wave function collapses into one outcome. No parallel universe is needed. It's the most widely accepted view. So which is it? Are we manipulating probabilities, or are we literally computing across the multiverse? Here's the thing. We don't know. And that uncertainty, that's what makes this so fascinating and so terrifying. Because if quantum computers are accessing other realities, then we have to ask, what are we touching that we don't understand? And more importantly, is something on the other side noticing us back? There are whispers unconfirmed, but persistent that during some of Google's quantum experiments, researchers observed strange patterns in what should have been random quantum noise, structured sequences, almost like responses. One researcher allegedly told a colleague, "We made contact. It wasn't supposed to happen." Then he disappeared from the project. Now, I'm not saying there's a massive cover-up. What I am saying is that when you're playing with the fundamental fabric of reality, strange things happen. And we're only beginning to understand what those things are. Okay, let's get technical for a moment, but I promise to keep it digestible. To understand how Willow is so revolutionary, we need to talk about the biggest problem in quantum computing: errors. Quantum systems are fragile, unbelievably fragile. Any tiny vibration, any stray electromagnetic field, even cosmic rays from space can cause a qubit to decohere, to lose its quantum properties, and just become noise. Let me tell you something about temperature. Willow operates at near absolute zero. We're talking about 15 millikelvins, that's 273.135 degrees Celsius, or about negative 459.64 Fahrenheit. To put that in perspective, outer space is warmer than the inside of a quantum computer. If you took a flower and dunked it in liquid nitrogen at negative 200 degrees Celsius, it would freeze solid and shatter if you touched it. That's cold, but it's still way too hot for Willow. The chip sits at the bottom of a dilution refrigerator, one of the coldest places in the entire universe, because at those temperatures, quantum effects can persist just long enough for calculations to happen. But even at those temperatures, errors happen a lot. Historically, the more qubits you added to a quantum computer, the more errors you got. It was like trying to keep 100 spinning plates balanced simultaneously. Each new plate makes the whole system more unstable. This is what's called the error threshold problem, and it's plagued quantum computing for 30 years. Google solved it. With Willow, they demonstrated something called below threshold error correction. As it turns out, Willow can fix its own mistakes faster than it makes them. It's like a car that repairs itself while driving at 200 miles per hour. In fact, Willow operates with 99.97% fidelity on single qubit gates and 99.88% on entangling gates. Translation: it makes about one error every 10,000 operations while working at speeds measured in nanoseconds. Your laptop makes more mistakes than that. It just has error correction built in that you never see. But here's the breakthrough. As Google adds more qubits, the system gets more stable, not less. Each qubit helps correct the errors of its neighbors. It's like having 1,000 tiny safety nets all watching each other. And they did something else remarkable. They performed 1 trillion measurements. 1 trillion. That's more measurements than all quantum computers in history combined. And they did it in weeks. This level of precision allows them to extract incredibly faint signals from an ocean of quantum noise. It's like trying to hear a whisper in a stadium during a rock concert, except the whisper contains the secrets of molecular structure. The most astounding fact is, this precision is what makes quantum echoes work. When they run time forward, poke a qubit, then run time backward, they need every single operation to be nearly perfect. Any drift, any error, and the echo collapses into randomness. But they pulled it off. They ran the experiment over 1 million times, gathering that trillion measurements, and the signal emerged clearly from the noise. All right, let's bring this down to earth. Why should you care about quantum computers doing impossible math at temperatures colder than space? Let me picture that in a different way. When the telescope was invented, it didn't just let us see farther. It fundamentally changed our understanding of our place in the universe. We went from thinking Earth was the center of everything to realizing we're on a tiny rock orbiting an average star in one of billions of galaxies. Quantum computers are this generation's telescope, but instead of looking outward at the stars, they're looking inward into the quantum realm where the rules of reality get weird. Here's what's coming, and I'm not talking decades from now. I'm talking 5 years, drug discovery. Right now, developing a new medicine takes 10 to 15 years and costs billions. Pharmaceutical companies have to synthesize thousands of potential drugs, test them on cells, animals, humans. It's trial and error on a massive scale. Quantum computers can simulate molecular interactions down to individual atoms. They can predict which drug candidates will work before you ever synthesize them. Diseases that are currently untreatable, we might find cures in a fraction of the time. Personalized medicine tailored to your exact genetic makeup, suddenly feasible. Material science. Want a battery with 10 times the energy density of anything we have today? Want a room temperature superconductor that revolutionizes power transmission? Want materials that don't exist in nature but have properties we can barely imagine? Quantum computers can search through possibility spaces that classical computers couldn't explore in the lifetime of the universe. Climate modeling. The climate is a complex system with billions of interacting variables. Better models mean better predictions. Better predictions mean better policy. We could finally get climate science accurate enough to actually prevent disasters instead of just reacting to them. Cryptography. Here's the double-edged sword. Quantum computers will break essentially all current encryption. Your online banking, your private messages, government secrets, all vulnerable. We're in a race to quantum-proof our digital infrastructure before quantum computers become powerful enough to crack everything. But they'll also enable unbreakable quantum encryption. It's an arms race happening right now. AI. This is where my brain starts to melt. We're already using AI to design better quantum computers. And we're using quantum computers to accelerate AI development. When quantum computers can efficiently run quantum machine learning algorithms, we enter territory that's genuinely hard to predict. We're talking about AI that processes information in fundamentally quantum ways, using superposition and entanglement as features, not bugs. Actually, there's a timeline I want you to pay attention to, 2025, which is right now, is the verification year, proving quantum advantage in real applications. 26 to 27. Fault-tolerant quantum systems that can run for extended periods. 2028. Commercially available quantum computing services for specific applications. 2030. Quantum classical hybrid systems as common in research labs as classical supercomputers are today. The organizations preparing now hiring quantum expertise, exploring applications will dominate their industries. The universe is under no obligation to make sense to you, but the winners will be those who figure it out first. But let's talk about the elephant in the room. Not everyone is celebrating. Here's what bothers physicists most. We're tampering with the fundamental fabric of reality, and we don't fully understand what we're doing. Dr. Sabine Hassenfelder, a respected physicist, points out that Willow's achievement, while impressive, was on a theoretical benchmark specifically designed to be hard for classical computers. The random circuit sampling problem isn't directly useful for anything yet. It's like building the world's fastest race car, but only testing it on an empty track. Cool? Absolutely. Immediately practical? Not yet. Then there's scalability. Willow has 105 qubits. Sounds like a lot. But practical, fault-tolerant quantum computing will need millions of qubits. And not just any qubits, ones that can operate reliably for hours or days, not milliseconds. We're not there yet. We're making progress, exponential progress, but we're not there. And then there's the darker implications. The same technology that will cure diseases can design bioweapons. The same systems that optimize clean energy can break into every bank simultaneously. What people don't realize is we're entering an era where the asymmetry between quantum haves and have-nots becomes a genuine security concern. Some scientists who worked on Google's quantum projects have raised concerns. A few left the project suddenly, some claiming they witnessed phenomena they couldn't explain. One researcher allegedly said, "We weren't just running calculations anymore. We were interacting with something beyond our understanding." Is this fear-mongering? Maybe. But here's the thing. Powerful tools are powerful regardless of intent. A hammer can build a house or break a skull. Quantum computing is the most powerful tool we've ever created. The question isn't if this technology will reshape civilization. The question is how we handle that reshaping. So where does this leave us? When I look up at the night sky, I know that we are part of this universe. We are in this universe. But perhaps more important than both of those facts is that the universe is in us. And now we've built something that lets us peek behind the curtain of that universe. Something that operates on principles so strange, so counterintuitive, that they challenge everything we thought we knew about reality. Is Willow accessing parallel universes? Is it just really good at manipulating probabilities? We don't know for certain. And that uncertainty is beautiful. Because here's what I believe. We are stardust brought to life, then empowered by the universe to figure itself out. And quantum computing is the next step in that journey. The next generation of innovators won't just use quantum computers. They'll think quantumly. They'll embrace uncertainty and entanglement, not as bugs, but as features of reality itself. This is the most important technology transition of our lifetime. More important than the internet, more important than AI on its own, because quantum computing enables everything else. It's the foundation that accelerates every other field simultaneously. Are we ready? Probably not. Is it coming anyway? Absolutely. And the choice we face is simple. Ride the wave or get swept away by it. Me? I'm choosing to ride. Because as terrifying as this might be, as strange and uncomfortable as quantum reality is, I believe in human curiosity. I believe in our ability to understand the universe, even when that universe operates on rules that seem impossible. The good thing about science is that it's true whether or not you believe in it. But the great thing about science is that it lets us turn the impossible into the inevitable. October 22nd, 2025, the day we broke reality, or maybe, just maybe, the day we finally started to understand it. If you want to stay ahead of the quantum revolution, hit that subscribe button. Because this story, it's only beginning. And trust me, you're going to want to see what comes next.